There is a layer of bubbles hidden 2.4 miles beneath Yellowstone, and for the last few years, scientists have believed it might be the single most dangerous thing in North America. They were wrong. It turns out that this layer of bubbles is one of the main reasons the supervolcano underneath one of the most visited places on Earth has not erupted. And almost everything you have been told about the threat sleeping under those geysers is built on a picture that was, until this past decade, hopelessly blurry. There is a roof of solid rock down there with an edge so sharp it should not exist. There is a substance pooling against that roof that behaves like neither a liquid nor a gas. And there are abandoned boreholes from the 1960s that erupted so violently they hurled a steel cylinder 50 feet into the forest. We will get to all three. But to understand what scientists actually found, you first have to understand why, for almost 100 years, nobody could see it. Let's start with what everyone believes. Yellowstone is a supervolcano. That word gets thrown around a lot, and it conjures a very specific image. A bulging chamber of glowing liquid rock, pressing upward, swelling, overdue. The last truly catastrophic eruption here happened about 630,000 years ago. People do the arithmetic. They notice the ground rises and falls. They notice the earthquakes, the steaming pools, the geysers that fire on schedule. And they arrive at a conclusion that feels obvious. The thing is filling up. The thing is going to blow. And maybe, if it is going to blow, we should do something about it. So here is the question that scientists get asked more than almost any other. Why not just drill into it? Drill a hole, let the pressure out. Tap the chamber like you would let the air out of an overinflated tire, or pop the lid on a pot before it boils over. It sounds reasonable. It sounds, on the surface, like exactly the kind of clever fix that engineering is for. And the strange thing is, people have tried to drill into Yellowstone before. They just weren't trying to diffuse it. They were trying to see it. And what happened to them is the first clue that the volcano does not work the way you think it does. In 1929, scientists from the Carnegie Institution arrived in the park with a drill. A geologist named Clarence Fenner sank 2 boreholes, one in the Upper Geyser Basin and one in Norris, hoping to read the rock beneath the famous springs like pages in a book. They were cautious. They drilled away from the well-known features, worried they might disturb them. They disturbed them anyway. Pools and fumaroles near the drill sites changed. And at Norris, the pressure coming back up the hole grew so fierce that the team simply had to abandon the work. That should have been the warning. It wasn't. Almost 40 years later, in 1967, the United States Geological Survey decided to do it properly. 13 holes across the major thermal areas, with better equipment and the lessons of Fenner's struggles in hand. They were confident, they were prepared, and the ground nearly killed them. The very first hole told them everything. As the drill bit dropped past 200 feet, the crew pulled the core barrel up through the pipe, and the cool water that had been holding the well calm suddenly gushed out. Within seconds, it turned to boiling water and steam, and the entire well erupted like a geyser. Scalding water and steam covered the platform and hid the controls the drillers needed to shut it down. One of the scientists later described it, with admirable honesty, as a shattering experience for all of them. And this was not a fluke. Over and over across those 13 holes, the wells surged into violent eruption the instant the pressure was disturbed. At one site, a steel core barrel, loaded with rock, shot up out of the drill string, bounced off the mast, and landed in the woods 50 feet away. The crews learned to manage the eruptions. They never learned to stop them. They measured pressures so high that the water inside the holes wanted to stand more than 200 feet above the ground. They recorded a temperature of 237 degrees Celsius at the bottom of their deepest hole, more than 1,000 feet down in Norris Basin. And several of the holes, despite every precaution, turned nearby quiet springs into erupting geysers. The people who drilled into Yellowstone did not relieve any pressure. They woke something up. And the ground had a way of healing over the wounds, which only made it more treacherous. Down in these hot systems, the rising water is loaded with dissolved minerals, and as it cools near the surface, it deposits them, like scale building inside a kettle. Over time, this seals the cracks and channels it once flowed through. Geologists call it self-sealing, and it means the plumbing is constantly closing itself off, trapping pressure in pockets that the drillers couldn't see coming. It also means the wounds from drilling never truly close on our terms. Decades after the 1960s campaign, in 1992, one of the old wells in Biscuit Basin that had been left accessible corroded through, and on its own, with no one drilling, it erupted boiling water and steam until crews could rush in and plug it. Back in 1930, when the Carnegie team lost control of their Norris hole, the only way they could subdue it was to pump 5 tons of cement down the casing. This is the reality the cartoon of the balloon completely misses. You are not poking a sealed container. You are puncturing a living, self-sealing system that pushes back, reopens old scars, and turns calm springs into geysers as the disturbed water finds new paths to the surface. And here is the part that turns the whole "just drill it" idea on its head. Because even if you wanted to drill all the way down to the magma itself, you couldn't. We know this because at other volcanoes, drillers have done it by accident. In Hawaii in 2005, a borehole on Kilauea ran straight into liquid magma. The hole didn't stay open, the magma flowed in and froze solid, sealing it shut. The same thing happened at Krafla, in Iceland, in 2009, and again in Kenya, in 2011. Magma is not air in a tire. It is closer to a furnace filled with molten glass that instantly hardens around anything you push into it. So the dream of sticking a needle into Yellowstone and bleeding off the danger collapses on contact with the rock. You cannot reach the magma, and if you disturb the shallow plumbing, it erupts in your face, which left scientists with a problem that sounds almost impossible. If you can't drill down to it, and you can't safely poke at it, then how do you ever find out what is actually down there? The honest answer, for most of the last century, is that they guessed. They had clues. They had the heat leaking out of the ground, the chemistry of the springs, the helium rising from deep in the Earth's mantle. They knew there was magma. They could even sketch its rough shape. But the picture they had was, in the truest sense of the word, blurry. To see inside the Earth, scientists use seismic waves, the vibrations from earthquakes that ripple through rock. As those waves pass through different materials, they speed up, slow down, and bend. And by recording them on instruments at the surface, geophysicists can reconstruct the hidden structures below, the same way a medical CT scanner reconstructs the inside of a body from beams passing through it. It is a beautiful technique. It is also, when you rely on distant natural earthquakes, soft at the edges. The waves arrive having traveled enormous distances. They smear. And so for decades, the magma beneath Yellowstone showed up in the data as something scientists openly called an amorphous blob, a vague smudge of probably melt somewhere around here. They knew the top of the reservoir sat somewhere between 3 and 8 kilometers down. But 3 kilometers and 8 kilometers are not the same answer. They are not even close. At 3 kilometers, gases come boiling out of the magma. At 8, they stay locked inside. The difference between those two numbers is the difference between a system that vents and a system that builds. And nobody could sharpen the blob until a small team decided to stop waiting for the Earth to shake on its own and to shake it themselves. This is where the real story begins. In the summer of 2020, seismologists from the University of Utah, the University of New Mexico, and Rice University came to Yellowstone with a plan that sounds, at first, slightly absurd. If the problem with natural earthquakes is that they are too far away and too messy, then don't use natural earthquakes. Make your own. Precise ones. Custom ones. As many as you need. Exactly where you want them. To do that, they brought a machine that looks completely out of place in a national park. A vibroseis truck. It weighs 53,000 pounds, and bolted underneath it is a heavy steel plate on a hydraulic arm. The truck lowers that plate to the ground, lifts itself up until nearly its entire weight is resting on it, and then makes the plate vibrate, not randomly. It sweeps through a controlled range of frequencies, pressing into the earth with something like 220,000 newtons of force for 40 seconds at a time. Each sweep sends a clean, predictable pulse of seismic energy down into the rock. A tiny, tailor-made earthquake on demand, and it does it again and again. 20 times at each location, at 110 different spots along the roads of the caldera. But making the signal is only half of it. You also have to catch it coming back. So, along the same stretches of road, the team laid out an array of around 600 small, portable seismometers, spaced every 100 to 150 meters. Hundreds of patient ears pressed to the ground, all listening for the echoes of the truck's pulses as they bounced off the structures below. And every part of this had to happen at night. Partly to keep from disturbing the millions of visitors who come to Yellowstone for peace and geysers, not for a vibrating industrial truck. But also because the night is quieter, and in this work, noise is the enemy. By day, traffic and footfall drown the faint returning signals. By night, in the cold and the dark, with the road empty, the instruments could hear the whispers coming back up from miles beneath their feet. And the difficulty of doing this on land is easy to underestimate. This kind of active imaging, where you create your own signal instead of waiting for an earthquake, has been done beautifully for years out at sea. A ship glides through the water, sending clean, well-defined pulses downward, and tows a long line of receivers behind it to catch the echoes. The water carries the vibrations in a smooth, predictable way, and the ship can run its survey in tidy, uninterrupted lines. Land is a different animal. You need a road, which means you can only put your sensors where the pavement goes. The vibrations scatter off the messy, irregular surroundings instead of traveling cleanly. And the surface world is full of competing noise, all of it threatening to bury the faint signals you actually care about. Yellowstone, oddly, was one of the few places this could work, precisely because a national park comes laced with quiet, accessible roads winding right across the caldera. The team ran their survey along a 30-kilometer stretch of road crossing the edge of a feature called the Sour Creek Dome in the northeastern part of the park, deliberately reaching for high frequencies from about 6 to 30 hertz, because higher frequencies carry finer detail and sharpen the picture. It was the marriage of all of it: the precise truck, the dense line of modern sensors, the quiet roads, and years of painstaking work to filter signal from noise that finally made the impossible photograph possible. Picture it: a heavy truck parked at a roadside pullout near the Continental Divide, headlights catching a sign, shaking the ground on purpose, while 600 hidden sensors strung out along the dark highway record the answer. They were, in the words of one of the scientists, causing their own earthquakes. And because they had laid out so many sensors and controlled the source so precisely, they could finally do something nobody had managed before. They could take a sharp photograph of the roof of the magma chamber. The results would take years to process, fighting through the noise to extract a clear picture. And when that picture finally resolved, it answered a question scientists had been arguing about for half a century. The answer came out in the journal Nature in April of 2025, and it was a single, startlingly specific number. The top of the magma reservoir beneath Yellowstone sits at 3.8 kilometers, about 2.4 miles down, roughly 12,500 feet beneath the surface, under the northeastern part of the caldera near the Yellowstone River. For the first time, the blob had an edge, and not just any edge. The transition was astonishingly sharp. The boundary between the ordinary rock above and the magma-bearing reservoir below was less than 100 meters thick. After decades of a fuzzy smear, somewhere between 3 and 8 kilometers, Here was a hard line, a roof, a clearly defined ceiling on the largest magmatic system on the continent, drawn at 3.8 kilometers, with a confidence that simply had not existed before. And the depth itself was significant because 3.8 kilometers is on the shallow end of everything scientists had feared. That sounds, on its face, like very bad news. A huge body of magma, closer to the surface than many had hoped, with a knife-edge roof. If the story stopped there, you would be right to feel a chill. But the team had not just located the roof. They had figured out what was pressed against the underside of it. And that is where Yellowstone stops behaving like a monster and starts behaving like something far stranger. To understand what they found, you have to understand what a magma reservoir actually is, because the cartoon in your head is wrong. It is not a cavern of sloshing red liquid. The shallow reservoir beneath Yellowstone is made mostly of solid rock. The magma is woven through it, filling the tiny spaces between crystals, like water soaked into a sponge or a slushy held together by ice. Most of it is solid. Only a fraction is actually molten. So, when the seismic waves struck the top of this reservoir and bounced back, the scientists read the strength and the character of those reflections like a fingerprint, and they tried to work out what mixture of materials could possibly produce that exact echo. Their first guess was the simple one: 2 ingredients, solid mineral crystals and molten magma. It didn't fit. The reflections were too strong, too distinct. A 2-part mixture of crystal and melt could not explain what the instruments were hearing. Something else had to be up there. So they added a 3rd ingredient, and suddenly the numbers worked. The missing piece was bubbles, not air bubbles, bubbles of supercritical fluid. Now, supercritical is a word that deserves a moment because it is genuinely one of the odder states matter can take. When you push a substance past a certain extreme of temperature and pressure, it stops choosing between being a liquid and being a gas. It becomes both at once, and neither. It can flow and fill a space like a gas, but it can be dense and dissolve things like a liquid. Down at the top of the Yellowstone Reservoir, the water, the carbon dioxide, and the sulfur coming out of the magma exist in exactly this in-between condition. They are not steam, they are not liquid, they are supercritical fluid, squeezed into a strange middle realm by the heat and pressure of the deep crust. And the new data showed that these supercritical bubbles are not scattered evenly through the magma. They are gathering, rising up through the molten rock because they are buoyant, and collecting in a thin layer right at the very top of the reservoir, pressed against that razor-sharp roof. A cap, a volatile rich cap, the scientists called it, a skin of bubbles at the ceiling of the supervolcano. And the reason this is the heart of the whole discovery is that the depth and the cap are connected. 3.8 kilometers is not just where the roof happens to be. It is the exact depth at which those bubbles can begin to form, go deeper. And the crushing pressure forces the gases to stay dissolved inside the magma, hidden. But at 3.8 kilometers, the pressure eases just enough that the gases come out of solution and rise as bubbles. Which means the scientists didn't just find the roof, they found the precise level where Yellowstone's magma begins to breathe, and whether that breathing is a warning or a relief depends entirely on one number. Here is where you have to brace yourself, because everything you instinctively feel about this is about to be inverted. Bubbles accumulating at the top of a magma chamber is, in general, a frightening thing. It is one of the classic steps on the road to an eruption. Gas builds up, pressure climbs, and if those gases are suddenly released, they expand with terrifying violence. As one of the lead scientists put it, trapped gases are exactly what make these eruptions so devastating, because when they finally decompress, they go off like an explosive. So, a cap of bubbles sealed against a sharp roof sounds like the setup for catastrophe, but it isn't. And the reason is the number the team measured for the cap itself. They found that this layer is only about 14% fluid. The other 86% is solid crystal. The bubbles are not packed into a swollen, pressurized dome straining against the rock. They are a minority, threaded through a mostly solid framework. And at that concentration, something quietly reassuring happens. The bubbles don't build up, they rise, efficiently. They float up through the system and escape, instead of accumulating into a dangerous, pressurized mass. The cap is not a lid trapping gas. It is a chimney venting it. And we can see the proof of that venting at the surface, every single day. Yellowstone is famous for the gas it exhales. Carbon dioxide and water vapor pour out of the ground across the park. The bubbling, sulfurous fury of a place like Mud Volcano is not a sign of an approaching disaster. It is the exhaust pipe. It is the magmatic gas, having risen from that cap 3.8 kilometers down, finding a channel and slipping harmlessly out into the open air. The system has a release valve, and it is wide open. When the magma rises from deeper in the crust, the volatile materials, the carbon dioxide and the water, come out of the melt, float to the top of the chamber because they are buoyant, and then, crucially, find a path to the surface and leave. So the picture that emerges is almost the exact opposite of the doomsday image. The shallow roof, the sharp edge, the cap of supercritical bubbles. Read in isolation, each one sounds alarming. Read together, with that 14% in hand, they describe a system that is mostly solid, well-behaved, and stable. The thing that looked like a fuse is actually a vent. And that single insight rewrites how seriously we should take the idea of Yellowstone as a bomb waiting to go off. It also makes sense of something that had puzzled people for a long time. If you have a really shallow magma reservoir, with its top at only about 4 kilometers, then of course the surface above it should be a riot of hydrothermal activity. Of course, there should be geysers and hot springs and mud pots and steam by the thousand. The shallowness of the reservoir explains the very features that make Yellowstone Yellowstone. The geysers are not a symptom of a sickness. They are the visible breath of a magma system close enough to the surface to make itself felt and stable enough to let its gases escape gently rather than catastrophically. For decades, scientists had been studying that surface activity from the outside, like doctors listening to a heartbeat through a closed door. Now, for the first time, they could connect the breath at the surface directly to the lungs 3.8 kilometers below. And that connection only deepens when you zoom out and look at the full architecture of what lies beneath the park. Because the cap and the roof are only the top of a structure that is genuinely vast. The shallow reservoir, the one made of high silica rock called rhyolite, stretches across an area something like 55 miles by 30 miles, and plunges from a few kilometers down to as deep as 10 miles below the surface. That is the body whose ceiling the truck and the seismometers just mapped. But it is not the bottom of the system. Beneath it lies a second, far larger reservoir made of low silica basalt, reaching from around 20 kilometers down to perhaps 50 kilometers deep. This deeper chamber is more than 4 times the size of the shallow one. And yet, here is the recurring theme of the entire Yellowstone story. It is barely molten at all, just a couple of % melt. The shallow chamber itself is only somewhere between 5 and 15% molten. Both of these enormous bodies, the rhyolite above and the basalt below, are overwhelmingly solid rock, with magma laced through them in small fractions. This is the truth that keeps surfacing every time someone takes a sharper look. The supervolcano is not a tank of liquid. It is a colossal, mostly solid mass, slowly cooking, with melt and gas distributed through it in ways that, until very recently, we could only guess at. And understanding that distribution, knowing how much melt there is and where it sits, is exactly what changes how we judge the hazard. You cannot assess the danger of a system you have only ever seen as a smudge. Now, at last, the smudge has structure. And that structure should make us reconsider some of the more dramatic ideas about what to do with Yellowstone, including one that came, surprisingly, from people who usually think about asteroids. Because not everyone has been content to simply monitor the volcano. Some have wanted to defuse it. A few years ago, engineers connected to NASA's work on planetary defense turned their attention from threats falling out of the sky to a threat sitting under Wyoming. One of them argued, strikingly, that the danger from a supervolcano is actually greater than the danger from an asteroid or a comet. And their proposed solution was, in essence, to cool Yellowstone down. The logic runs like this. A supervolcano is a giant heat engine. If you could pull enough heat out of it, it could never reach the threshold for an eruption. Their concept was to drill, not into the top of the chamber, which they recognized would be reckless, but in from the sides, from outside the park's boundaries, and to pump water down at high pressure. The water would circulate, absorb the heat, and return to the surface at around 350 degrees Celsius, slowly, year by year, draining warmth from the magma. As a bonus, that hot water could drive turbines and generate cheap geothermal power for tens of thousands of years, helping to pay for a project estimated to cost billions. It is an audacious idea. It is also, by the admission of its own framing, a plan that would take an almost unimaginable span of time, cooling the system at a rate of perhaps a single meter a year over tens of thousands of years. Nobody who began it would ever see whether it worked. And the scientists who actually monitor Yellowstone have serious doubts that it would work at all, and real fears that it could backfire. Remember what the new imaging confirmed. This is a mostly solid system, fed by a hotspot deep in the earth that supplies a relentless, steady stream of heat from below. Trying to cool it by trickling water into the subsurface, one analogy goes, would be like trying to cool a pot of boiling water by adding cold drops one at a time while leaving the burner on full. The heat source never switches off. Worse, the very act of meddling could be dangerous. Rapidly dropping the pressure on magma, or chilling it, can cause its dissolved gases to come rushing out of solution, the way a fizzy drink erupts when you crack the seal. In other words, an attempt to make Yellowstone safer could nudge it the other way. And then there is the simplest objection of all. The system already cools and vents itself, naturally, through exactly the hydrothermal features the new study illuminated. The water, seeping down through cracks, heating, and rising back out, carries away most of the heat on its own. Yellowstone is not a sealed bomb desperate for someone to defuse it. It is an open, breathing system that has been managing its own pressure for a very long time. Drilling to stop an eruption, as the observatory bluntly put it, is a non-solution to a non-problem. And here is the part that ties it back to where we started. The same drilling that can't save us is also the drilling that fights back. We have seen what happens when you sink a hole into this ground. It erupts. It throws steel into the trees. It is not waiting to be tamed. So if the great eruption is not the immediate danger, does that mean Yellowstone is harmless? No. And this is where the story turns one more time, because the real, present hazard beneath your feet in the park is not the supervolcano at all. It is the water. On the morning of the 23rd of July, 2024, near a feature called Black Diamond Pool in Biscuit Basin, just a couple of miles from Old Faithful, the ground exploded. Without warning, no instrument caught a precursor. A plume of hot water, mud, and rock fragments blasted 400 to 600 feet into the air while visitors ran for the boardwalk. The explosion tore up the walkway and scattered boulders, some of them weighing hundreds of pounds. By extraordinary luck, the blast was angled away from the people, and no one was hurt. This was not a volcanic eruption. No magma was involved. It was a hydrothermal explosion, and it is the most common dangerous event in Yellowstone by far. The mechanism is almost mundane until you see its power. Water, trapped underground and superheated, sits in a confined space. Mineral deposits gradually seal the pathways around it. Like scale clogging a pipe, pressure climbs. And then, in an instant, the seal fails. The superheated water flashes explosively to steam, and the ground bursts open. It happens with little or no warning, which is precisely what makes it so hazardous. These events occur somewhere in the park most years, usually in the backcountry where no one notices. But they can be enormous. How enormous? Consider Mary Bay on the north side of Yellowstone Lake. It is a crater roughly 2.5 kilometers across, and it is the largest hydrothermal explosion crater known anywhere on Earth. It formed about 13,000 years ago, and the leading explanation for what triggered it reads like a disaster novel. A large earthquake on the lake floor caused the lake level to drop suddenly by around 14 meters. That abrupt drop in pressure on the superheated water below was enough to flash a vast volume of it to steam at once, blowing out a crater more than 1.5 miles wide. The same lake hides the 3 largest hydrothermal explosion craters on the planet, and sediment cores pulled from its floor have recorded 16 separate explosion events over the last 13,000 years. And those cores told a subtler story than just a list of blasts. They revealed that 2 very different kinds of hydrothermal systems produce these explosions, and that the difference matters enormously for how violent they are. One kind is driven by neutral alkaline chloride fluids, the same chemistry that feeds the great geysers near Old Faithful. When that water flashes to steam, it produces the largest explosions of all, the ones that carve out craters miles wide. The other kind comes from vapor-dominated areas, more like the bubbling ground at Mud Volcano, and tends to produce smaller, though possibly more frequent, blasts. The cores even showed that the 2 biggest events in the lake's history were set off in completely different ways. One, at a feature called Elliott's Crater, was triggered around 8,000 years ago when a major earthquake ruptured a hydrothermal dome. The other was Mary Bay, set off by that sudden collapse in lake level. Same catastrophic result, 2 unrelated triggers, which is exactly why these events are so hard to forecast. That difficulty of timing is its own frontier of research, because dating these explosions is notoriously hard. The debris they leave behind rarely contains the kind of material the usual dating methods need, and it gets reworked and altered over time. So, scientists have turned to a clever technique called luminescence dating. And the way it works is best understood as a battery. Buried mineral grains slowly soak up energy from the natural radiation around them, charging up over thousands of years. Heat or sunlight drains that charge back to zero. Before a hydrothermal explosion, the grains sit in hot fluid, constantly heated, held permanently at empty, like a dead battery. The instant the explosion hurls them up onto the cool surface and buries them, the heating stops and the battery begins to charge. Measure how much charge has built up, and you can read how long ago the grains were thrown out, which is to say, when the explosion happened. Applied to a vast crater in the lower geyser basin called Pocket Basin, the method pinned the blast to roughly 13,900 years ago, right at the end of the last ice age, hinting that the retreat of the glaciers and the pressure changes that came with it may have helped pull the trigger. These are the eruptions that should actually be on our radar. Not the once in hundreds of thousands of years supereruption, but the sudden, local, unpredictable steam blasts that can happen somewhere in the park in any given year. And the unsettling thing about them is exactly that unpredictability. Which is why, even as scientists celebrate finally seeing the magma roof clearly, much of their energy is going into a different challenge entirely. Learning to hear these explosions coming. That effort, too, runs through holes in the ground, though of a far gentler kind than the erupting wells of the 1960s. Between 2007 and 2008, scientists drilled a small network of boreholes in and around the caldera, not to extract anything, but to plant instruments deep enough to feel what the surface cannot. The sensitivity of what they buried down there is hard to believe. Strain meters, cemented into the bottom of the holes, can detect a change in the shape of the surrounding rock as small as 4 picometers. To put that in perspective, that is roughly 10 million times smaller than the width of a single human hair. Nearby, tilt meters measure changes in the ground's tilt of less than a millionth of a degree, so sensitive they pick up the pull of the tides and the tremor of distant earthquakes on the far side of the world. Borehole seismometers, buried away from the noise of the surface, can catch the faintest microtremors, the tiny shivers caused by waves lapping in Yellowstone Lake. Drilling these holes was not easy. The engineers ran into geothermal fluids hot enough to threaten their instruments, water that came up between 67 and 91 degrees Celsius, laced with chemicals corrosive to electronics. But the network they built turned Yellowstone into one of the most closely watched volcanic systems on Earth. And newer additions, like an infrasound array, installed in 2023 to listen for the low rumble of hydrothermal blasts, have already detected explosions that no human witnessed, including one in a geyser basin that would otherwise have gone completely unrecorded. The landscape is changing in real time, and sometimes the instruments catch it being born. In April of 2025, geologists returning to Norris Geyser Basin after the winter found something that hadn't been there the previous autumn. A small new pool, about 4 meters across, filled with warm, milky blue water, ringed by rocks and freshly thrown silica mud. Working backwards through satellite images and the faint acoustic signals from the infrasound array, scientists reconstructed its birth. There was nothing in October. By early January, there was a small depression. By mid-February, there was a pool. And the weak signals suggested it had not formed in one violent burst, but through a series of small events that began, of all dates, around Christmas of 2024. A new feature in one of the most dynamic corners of the park, quietly assembling itself over the holidays, recorded by sensors sensitive enough to hear it happen. This is the texture of the real, ongoing Yellowstone, not a countdown to apocalypse, but a restless, breathing landscape constantly remaking its own surface. We have, in effect, wired the supervolcano. We can feel it flex by the width of a fraction of an atom. And against that backdrop of exquisite sensitivity, the achievement of the vibroseis study comes into even sharper focus. We did not just get better at listening to Yellowstone. We learned to ask it questions and to read its answers down to a 100-meter thick line 3.8 kilometers underground. Step back and look at how far this has come. For most of a century, the inside of Yellowstone was a guess wrapped around a few hard clues. Early drillers tried to touch it directly and were driven back by scalding eruptions. Seismic imaging gave us a shape, but a soft, smeared, arguable one, an amorphous blob that could be 3 kilometers deep or 8, with everything that difference implies. And then, in a single decade, the picture snapped into focus. Better seismometers, small enough to scatter 600 along a road. Better methods to dig the signal out of the noise. And the simple, almost cheeky idea of building your own earthquakes with a truck rather than waiting on the Earth's. One of the scientists compared the leap to the jump from old cameras to modern digital ones. The same scene suddenly rendered in a resolution that reveals detail nobody knew was there. The blob became a roof. The roof grew a sharp edge. And against that edge, we found a breathing cap of supercritical bubbles that turned out to be a sign of stability rather than doom. We replaced fear with understanding, and the understanding was more reassuring than the fear had ever allowed. But the most important thing about this discovery is not really about Yellowstone at all. It is about what Yellowstone lets us learn. In many ways, it is a laboratory volcano. It is enormous, it is active, and yet it is accessible, crisscrossed with roads, studied for over a century, sitting quietly enough that scientists can spend their nights vibrating its surface without anyone getting hurt. Most of the world's most dangerous volcanoes are nothing like that. They are remote, or violent, or hidden beneath the sea, like Santorini in Greece, or restless beneath crowded cities, like Campi Flegrei in Italy. Those are the volcanoes that can kill on short notice, and those are the volcanoes that are hardest to study. So, when we learn to measure something new at Yellowstone, when we prove that it is possible to detect a thin cap of accumulating bubbles atop a magma reservoir, we are building a tool that can be carried to the places where it might one day save lives. The technique that mapped Yellowstone's roof can, in principle, be pointed at volcanoes that genuinely threaten people, reading their hidden caps, judging whether their gases are venting or building. Yellowstone is the practice run, the patient, well-behaved giant that teaches us how to read the dangerous ones. And yet, for everything that snapped into focus, the most honest ending to this story is that the mystery is not solved, it is sharpened. We now know the depth of the roof and the makeup of the cap with a precision that would have seemed impossible a decade ago. But knowing the top of the system in such detail only throws into relief how much of the rest remains uncertain, how the melt is distributed through that vast, mostly solid reservoir, how the gases move and gather and slip away over years and centuries, how a system this large will respond, slowly, to changes we cannot yet predict, and whether the things we have learned to measure here will read the same way on a volcano with a very different temper. The picture is no longer a blob, but it is also not finished. It is a high-resolution snapshot of a single, restless moment in the life of something far older and slower than we are. The roof is real, the cap is real, the stability, for now, is real. We drilled, we shook the ground, we listened in the dark, and we finally saw the ceiling of the giant. And the giant, it turns out, is breathing easy. For now, that is enough. The rest, like the deep heat itself, is still rising slowly toward the light. And we will keep watching, instrument by instrument, night by night, until we understand the whole of it. Because a mystery this large, sitting this close beneath our feet, is not something you ever really stop trying to solve.